general. How do you hear? Or let's maybe start. What do we hear? So what is that?
Sound waves.
Sound waves, right? And so if you, like back in the days when I was a child, put up the phone, there was this tone, at least in Europe, I don't know what's here, it's like 440 hertz. It's like the tuning note for an orchestra. So this is like only one frequency. But when I talk, there's like many frequencies, right? So it's if you were to plot it as a function over frequencies and amplitudes, this is then called spectrum. And there are fancy apps that just do it for you. And so if you're lucky, my cell phone is
it was connected a second ago. I think the cell phone went to sleep. Yeah.
Very nice. The Zoom should also make it work. Or if somebody else could just point a laptop on this side, I think that would be nice. Just with a webcam and something.
I'll connect with you.
Thank you. Yeah. So if I open this app here, I just downloaded it. It's called Spectroid. It's just one out of many. So what you see here in the upper bar, I just try to rotate it, is, as I said, the plot where you have the frequencies on the x-axis and the amplitude on the y-axis. So if I try to speak, you see that it's vibrating. If I try to have a constant sound, it's like ah. You see there are certain frequencies, right? Some maxima. So if I try to freeze it now, it's like ah. Okay, no, I cannot freeze it. Ah. Okay. But
It froze on its own.
Okay, once more. Ah. Okay, I'm a really bad singer, but so what you see here is like maxima. If I were a perfect singer, I could eventually squeeze all the energy in only one bar. But since my voice is trained enough, you see multiple of these bars that are like higher harmonics of the frequency. So that's also why, for example, the piano sounds so wonderful, because you have like all the different frequencies coming at the same time. And so this concept of Fourier optics is very similar. So you have two different spaces. You have the real space, that's basically what you hear, and you have the frequency space, that's what you see here. So you can convert, so there's a function which goes from the real space, like what you hear, the time domain, into the frequency domain, where you have basically a histogram or like a plot where you have frequencies or the amplitude. And so an analogy is that now, so the ear is working very similar. So there's, I'm missing all the English words, so forgive me, but there's a path in your ear which is like a spiral, where the nodes or like the frequencies are going in. There are little hairs detecting these frequencies. So this is like a small tuning fork. And so they start wiggling around for each of these hairs, a different frequency, and then there's like a little nerve connected to this tuning fork, and then your brain is then demodulating the different frequencies into something that eventually sounds like a tone. So it's what's exactly going in there is like crazy, but so what that means is your ear is translating time domain, so frequency over time, the amplitude over time, into frequency domain, because it's just modulating it. And so why is that helpful? So what's plotted here, my phone will stop again, is the frequency from 0 to 30 kilohertz. And so what we usually hear is something in between 0 and 20 kilohertz. And so that means our ear is something like a low pass filter. So we can hear between, I think, 50 and 20 kilohertz, somewhere around this. And that means we have a filter. You can also tune your filter, for example, with electronics, so that you have a band pass that only passes through certain frequencies, or suppress certain frequencies. For example, sometimes you see that you want to suppress the 60 hertz, which is the power grid noise and all these kind of things. And so that means you have this function that translates real space into Fourier space, and then you have a function that can filter this Fourier space and eventually go back to the real space. So why is that helpful? So if I were to plot the frequencies, and I would only have a single frequency. So what does it mean? what I said, so this is our frequency, this is our amplitude, and I said our ears having a single frequency. Let's say when you pick up your phone, it's 440 hertz. And so if you go to the frequency domain, this is the amplitude, then you have a single peak at 430 hertz, where you only have this information. So that means you relate this frequency to this amplitude. Imagine now I have a second one at, say, 880 hertz. So how would I plot this here? Any idea? Yeah, yeah.
It's like more.
Yeah, how much?
It's like that. 1 over
1 over 2, so double.
Yeah, that.
So something like that. So that means, so if I plot something here, you have basically this here, and if I have all the different frequencies here in the frequency domain, that means I'm adding all the different sinusoidal waves in the time domain. That means I have a constant. And so this is now the 1D case, so one-dimensional. And imagine a Fourier transform in optics does the same thing, but now also along the x and y axis. So you have to imagine that you have this information not only in the time domain, or like in the x-axis, but also in the y domain. So the Fourier transform ability of a lens, for example, can imagine start again with the one-dimensional case.
Yeah, so just to think about the completeness of this theorem, what Fourier actually showed in the original form is you can take any function of any arbitrary complexity, and if you're allowed infinite number of time series allowed to be added, this representation of frequency is actually complete, although you need infinite number of frequencies to form that function. And so this is why this idea is very powerful from a context of compression, is that you get to choose how many types of frequencies that you will add to be able to form a partial picture or truly, and in optics, as close to the actual image. So this is not, in its simplest case, this is not an approximation, which is what's happening in the optics, but for free.
Yes.
The lens is actually doing this for you.
Right, and I'll show you that in a second. So this is now our pattern. Let's assume this is a sinusoidal structure. So if I were to draw a line along this direction here, and I plot it here, it's a sinusoidal. So it means it has a certain frequency. Let's say when we think about the 430 hertz, we can also think about something like 1 over meter. So that's the spatial frequency. So let's say 1 over 10 micrometer, for example. And so a lens now does a Fourier transform from the 2D pattern into the 2D Fourier spectrum, similar to what our ear does. And so how would it look like? So if I were to Fourier transform this here, so I think in signal theory you put something like this here, you have again this one peak for this one frequency, but now it's like y and x. And so you have this one peak right here. And since we have symmetry, we also have it here, but with negative notation. We don't care about this now. And so the Fourier transform in 2D, also in the 1D case, is always symmetric for the positive and negative frequencies. So, and to prove that this is right, I downloaded a second app, which is from, I think, a student in Laura Waller's group. I think it's not available anymore. It's called Fourier Filter Camera. It does the same thing. If it's not stopping, okay, so. Okay. So, what you see here, obviously, is just the camera on my phone. And so if I have a structure now, so that's what I want to have this grating for. Thank you.
Clearly, we made this grating for this demo.
Can you assist me by just holding it here? Thank you. We don't get any aliasing. So if I, can you come a bit closer? Sorry. Perfect. Thank you so much. So we see this grating here, and if I go to Fourier space, you would expect frequencies. Okay, that's maybe from the dialectical point not super smart because it's a two-dimensional grating. That's something I found here. So you see these blue dots, right? So in every dot there is this one frequency. And there are multiple because it's, as I said with my voice, higher harmonics in a way. So there's some funny thing going on.
And then
So
try tilting your grating. Yeah, you see that? That's the rotation.
yeah.
Because now in the XY plane, it's a projected plane.
Oops. Yeah. And so so now what we want to try to do is like we imitate our ear by limiting the frequency bandwidth along a certain direction, and that's actually very cool. So they implemented this feature here. Another thing, so if I zoom in, that means the frequency goes down. So that means the points shrink. So the frequencies go the center. I should have said the 0 point is in the center. So if I go now further away, means like the frequency, going back to real space, the grating gets smaller and smaller, meaning the spatial frequency goes up, and that's also causing my camera or my cell phone breaking. Yeah, the app is it's funny. Anyway, let's try it again. So going back to, you do a very good job. Appreciate that. Thank you. So we go again from real space to Fourier space. We see these spots here, and what we do now, we just delete everything here along this direction. So that means, similar to our ear, we cannot see these frequencies. So what would you expect what I'm doing now? What would you see now when I'm going back to real space? I'm blocking these frequencies.
And let's give people time before you show the picture.
Yeah.
Yeah. So
But
you don't have to be right. You can just blurt out whatever
Yeah.
you might think will happen to the picture, which is the real space, when you have made this manipulation in the Fourier space. You have blocked a certain frequency that was present in that picture. Yeah. Anybody? You can just say it. It doesn't have to be right. That's the whole principle of the class.
yeah. So imagine.
Clearly, if you think about what those lines were coming from, what is the most common component in that picture that is giving rise to these spatial frequencies?
Or maybe again thinking about the ear. What happens if I block the frequency range between, say, 1000 hertz and 10 kilohertz?
This.
Yeah.
You don't hear anything, right?
Yeah.
And that's also happening now here. So if I go back to real space,
Whoa.
you don't see. Okay, this is like all the artifacts. Okay, this is weird. I have
It's
to,
too complex
I
a
have
grid
to-
because you cannot eliminate all of them.
I have to draw better. So and then I also have to hold my phone straight so that it's like
It's
really
not dynamic.
Okay. Okay, so well, you see higher frequencies, but what you mostly see is like the lines that go like horizontally, right?
But the vertical lines have disappeared.
Yeah, only the very high frequency. So I have to go back to real free space and just block everything here, basically, and hope that this is enough. Okay. Let's see. Almost.
Yeah.
So, and what's happening now if I rotate this thing? So you see, the frequencies they stay like that, right? So because the grating remains stationary, just my camera rotates. So now
And so, but you're blocking with the red, you were blocking the horizontal
yeah.
spots, but you're accentuating the horizontal.
Yeah, so what I do here, so I can now rotate the phone. So basically it's kind of an edge detector along the vertical direction, the horizontal direction. So everything that's along the vertical direction can transmit the lens, and everything else is blocked. So what you see here, I'm rotating, and whenever it's like perpendicular to the stripes, you see it again.
Yeah, I guess maybe the same question actually. Why is because you blocked on this, like when you were blocking it on your phone, it was
Yeah.
appearing horizontally.
Yeah.
So is the Fourier plot there inverted compared to the XY axes of the real space?
Okay, so okay, that's yet another thing. So I think that's something which needs more explanation.
Oh, you're saying okay. Never, I
So
think I see. Yeah.
I tried to explain that based on what I told you last time, just quickly, and then I wanted to move on. So what I said last time, why is a Fourier lens a Fourier transformer? So imagine you have the sun coming from very far away, sending out light waves that are almost perpendicular. so like parallel to each other, but perpendicular to the lens. So like an ordinary lens, focus of it to one spot. And so if you have an oblique ray, it's getting focused basically here, always in the focal length. So if you assume that these different rays are coherent to each other, meaning they can't interfere with each other, that means you have these three dots, and they relate to the Fourier transform. Okay, so this link, I think need to have the slides. Yeah.
I guess I have a thought
So
maybe, which I
today-
think answered my own
Sorry.
question.
Yeah, go ahead.
So I guess if I were to draw on the board, so I think the question was basically like, we blocked out points that were along this horizontal x-axis of the Fourier, but the lines that remained were the lines that were horizontal, so it's kind of like non-intuitive, right? Like we feel like we're blocking horizontal, but then we see horizontal. But if you were to, for example, take this structure here and do a Fourier transform on this structure, in which dimension, or in which direction, if this is y and this is x, in which direction is there a sine wave
Yeah.
that you would see if you slice this?
Yeah,
Yeah.
right.
So
Okay, do people understand the concept? Sorry.
another approach. So
Okay.
So I try my best. So think about the interference I showed you last time. So you have a plane wave this direction, you have a plane wave this direction, and if you just have these two contributions, let's say wave 1 and wave 2, and we said the resulting wave is basically wave 1 plus wave 2, so they can interfere constructively, destructively. So if you have 1, 2, they just give the this here, so plus. So that's the thermal the concept we used. So it means like whenever you have the amplitude high, they give an even higher contribution. That means like in all these lines here, which is the wave traveling along this direction, we just sum up the values here, and all of a sudden what we have here is a grating. So grating along one direction. So you have to imagine it points outwards, the board. And when we now think, this is kind of an image of a grating. If we now place a lens here, in the focal length of the grating here, so in the front focal length of the lens we place the grating, or grating is represented as the summation of two waves, or also three waves, and this is better. So then we have wave 1 plus wave 3, and then meaning what I said, if you think about what does the lens do, this one wave just focuses on a point here, this one wave here focuses on a point here, and this other wave focuses on a point here. So let's say the explanation is not quite right. So, but the interference pattern caused 3 dots, and these 3 dots directly correspond to the Fourier transform of the incoming field. And so a grating, a perfect grating of a sinusoidal shape, so where you have on, off, that causes a Fourier transform of a 0 peak and a plus peak and then a minus peak. And believe it or not, we can visualize that. We can take a grating, which about on Amazon it has it says 1,000 lines per millimeter, and so if we illuminate it with a coherent light source, it's a laser pointer. I just found a lab, green one. What you see is then, so this is the plane wave which is going out of the laser pointer. And if you now put the grating in here, you see it's splitting into the plus and minus first order and still has the 0 order. So what's happening now is the different waves interfere on the board as the plus and minus first order. And this is only visible very far away, as I said, so the Fourier transform basically does conversion from very near to very far away, ideally infinitely far away. And what the lens does is basically it just takes everything that's very far away to the focal plane. So imagine the sun is almost infinitely far away, and you can focus it using a lens in the focal length, and then you basically can think of getting something from very far away into the focal length. So I don't know whether this is clear.
Just a term to remember is that's called the Fourier plane. So the little space in which Benedict did that example electronically, but the purpose of showing that example was you don't need electronics to do that. Just using a light source and a lens and a blocker, the exact same thing that happened there, although that was happening computationally, actually happens in real life. And your focal plane is that Fourier plane. So if you were to then put a mask in your focal plane, you would literally be doing what you were doing by blocking those frequencies.
Yeah.
And that's the tricks that you want to play in being able to jump from real space to Fourier space to real space to Fourier space. And whenever you want to do that, you want to be just, a lens gives you that computation that we normally would do in acoustics. I don't know if there is an equivalent of a mechanical object that does for sound, for what lens does for light. There does not, I can't think of one.
Oh.
Yeah, which is really funny. I mean, it really is computation that comes for free. And this is why this concept is a very powerful one in designing optics, because you really are doing these types of tricks as you play along in the real world.
Yeah.
And so the just thing to keep in mind is where in this optical setup is your Fourier plane.
And maybe, I think it's really bizarre what I'm talking about right now, so feel free to ping me afterwards. Maybe the very last comment about like optical resolution. So we started now with the waves and come to the Fourier plane, but we can also do it vice versa. So if you have now these three spots in the Fourier plane, and you have a lens, and you assume each of them produce a plane wave according to the angle they go through the lens. So you have the three plane waves. They also, in the Fourier plane, here, there, they form again interference pattern according to the angle they go through the lens. And so that means if you take these points here further apart, the angle here will just go higher. And that means the frequencies of that means like the points where the different waves start to interfere, they shrink more and more. So this is maybe the relationship between the sound I'm talking with, and then the ability of information you can transfer through an optical system. Okay, long talk. I want to have about like 10 minutes.
But I think what we'll do today is we'll actually do some demos where
Yeah.
we'll put some lenses and you'll kind of get a chance to see
Right.
how to manipulate a Fourier space and actually get a picture that's surprising.
Right.
And most filters in Photoshop, if anybody's used Photoshop, this is how it works. When you say I want to contrast, when you say I want to change enhancement, they're not doing it on a bitmap. They're actually doing it all in Fourier space.
And so the two concepts you have to stick with and then get an intuition how that really works is a lens, a perfect lens has a property called a focal length, and it means it's usually symmetric, so before and after it's the same length away, and you can go from a point to infinity and from infinity to a point. So these are the two concepts you have to keep in mind for now. And that's also the core idea about what I'm trying to show you now.
I know in terms of sound filter, you said there's nothing equivalent in sound, but isn't white noise sort of that?
So you can think of white noise basically having all kinds of frequencies, and in a classic sense in physics, when we say white noise, pink noise, what what you're really trying to say is what is that distribution of these types of frequency. So white noise is a characterization of a type of sound which has lots of frequency components. But what I was trying to ask is, just like a lens can do this Fourier transform for free, is there a I mean, our ear does it, but a ear is a very complex device. There are many, so it is, one example is ear is a physical implementation of what I was thinking about, but are there other mechanical components that would do that frequency transform without just mechanically? But white noise, you should think of it as, in the picture world, white noise is just like a photograph of a certain kind, because it has certain representations of those frequencies.
So if, instead of using white noise,
Yeah.
which is, I understand now the wrong term, if you used just certain frequencies, then you wouldn't hear those frequencies as part of, say, the music that was coming at you.
That's correct. If you were in Fourier space, block those frequencies, that instrument or that particular type of sound would disappear. And the demo, if this grid did not have this complex multi-frequency structure, when you do this demo for grids that don't have two widths, you would have actually seen, what was your name again? Steven standing right in front where the grid will disappear, literally. And it's a freaky kind of a demo, but it is done that, oh, where did it fill that information? But it literally wipes that information from, this happens to be a grid that's too complex, and so the pattern that you need to draw in the mask needs to be far more complex to make sure, and has to be pixelated in a certain way to cherry pick and remove certain kinds of things. This is also very simply, if you were to just draw a giant blob in the middle of that Fourier space, what you have done is remove certain types of frequencies, and this is what blurring is. When in Photoshop you drag that thing and say, make my image blurry or sharp, all you are doing is drawing a circle, either inverted, you can either keep just the frequencies that are right in the middle or the outside. And so blurriness of an image is removing high frequency component of information.
So just to give the analogy of the optical filter, maybe. So the experiment I just did with the laser integrating was maybe not very obvious. Sorry. What I did is I have my laser. It's sending out paralight by means of almost collimated beams. And so then you have this object in the way that's diffracting the light. So I think that was what I showed last time. So you have many different, or like small curvy points here that send out point sources, and in the end they will sum up to a discrete pattern, what you saw at the whiteboard. So we saw that with our eyes because that was nicely pictured on the whiteboard, but we cannot see the image of the grating. So in order to image this grating, so if you want to know that is 1,000 lines per millimeter, we have to have an optical system, and that's working the way that you place a lens, knowing that this lens here forms in the focal length here, the three distinct points here. You place another lens here, again focal length here, and I would need to have another whiteboard here, because then these points here, because it's just a mirror, know that these form the plane waves again, and they interfere to form a kind of image of the grating. Does it somehow make sense?
And then that's when you have taken a picture.
Yeah.
So imagine that's what you record, because often enough with an optical system what you want to do is to transform information that's coming in, go into Fourier space, do a bunch of stuff, but then you convert it back into real space.
Yeah.
And that's the picture that you see on your camera, for example. That's where you would place an imager. But you have this beautiful thing that you can do by implementing things in the middle to modify what you're interested in capturing. And so when you think about a confocal microscope, it is a type of a mask. Like you can implement a pinhole, you can implement many kinds of patterns inside that the time your image is in Fourier space.
Right. So maybe sense to motivate it a bit more. So we have our 3 points here in the Fourier plane of our lens. And we place a second lens here, and this is just doing in the inverse Fourier transform. So from the grating, which has one single frequency, to the fluid plane, we do a Fourier transform, and here we do an inverse Fourier transform. Just assuming that. And so these waves come out of this whole system here, and they again form interference, as we know that from here. And now the resolution of the optical system is basically determined how much, or what's the angle, the maximum angle we can pass through the lens. And since the lens is a finite size, you cannot be any higher in angle than this here. So that means like this formula I was showing last time, like the d lambda over 2 is funny, it's just this here. So this is the formula I was pointing on the board last time. This is basically the angle at which what's the ability of collecting information. So if you have a lens that is basically collecting all the information, it's still only able to collect information from one side of the room. And so that you're always limited by this formulation. And so the back lens cuts down information somewhere here. So if we have a grating that's like 1,000 lines per millimeter, it has maybe, it cannot go through the lens anymore, and in order to form an image, you have to have interference of at least 2 different components. That means if I have a lens that just is too small, this contribution is gone, this contribution is gone, and so this wave is gone. And what you end up is just a plain wave, and this just at some intensity.
And
So-
then the analogy to music here would be, is if you have all kinds of frequencies that you're listening in an orchestra, but then you put a filter that throws away certain kinds of frequencies, and that's the equivalent of resolution of an image in the context of music. You cannot appreciate the complexity of the music because a certain class of frequencies have now been thrown out. And there is no way around this until super resolution came along, because howsoever you collect these frequencies, there are certain frequencies that will get thrown out. Because the larger the lenses get, harder it gets to make them perfect.
Right. And yeah, so if you have any further questions, I think we should then maybe discuss it afterwards. I'll just continue with a quick walkthrough why this concept is actually super helpful and useful for optics. And we can use this in Frugal optics as well. And I usually motivate it the way that, well, everybody knows what that is, right? So this is a hammer, and everybody also knows what to do with it. And so I think not only us in our lab, but also I think many people here in Manu's lab, including Manu of course, they try to make microscopes as easy to use as a hammer. Judging from just the random pictures I took from Twitter, that's not always the case. So the upper one is a rendering, the lower one is actually not a rendering. So this is a quantum photonics entanglement experiment where they did some encryption. So people knew what they did there, and it's well, for me, even though I know what optics is, it's impossible to replicate that. So microscopes, in most cases, either you buy it or you build it, they are like black boxes. And so what we try to do, of course, is like bringing the 2 different disciplines together. I think that's what I was motivating last time. The problem is, if you buy a microscope, it's either too expensive, it's not really accessible, you cannot manipulate it, or you can simply not buy it anymore. And so we have to find solutions, and luckily there are some solutions. So there's just some I put together, like Foldscope, of course, Octopi or Squid. There's also the open vector. This is actually fully 3D printed based on vector bearings, which is quite amazing. Some more fancy stuff and some counterwave zoom thing, whatever. But so what we tried to do with the UC2 stuff is basically fusing these different worlds around the Fourier optics. Why is that helpful? And I think I just skip many slides and go to that one, I guess. Oh no, not quite. Yeah, this one. So I said I am an electrician by training. So back then when I started my apprenticeship, I had to do this many times. So developing an electric circuit board. And usually what you do is like you're sketching out the schematics, you build a PCB, you fabricate it, program it, and then in the end it always fails. Like the first approach never works. And use this just for a single LED to bring it to blink takes ages. And then when I was done, there was this little guy, the Arduino, and you plug it in, and this LED is blinking, and then you can change the frequency, you can change basically whatever, because there's a huge open source community who's building tools around it, and you can use all kinds of different boards, and it's just insane how cool this thing is and how much it contributed to open science and to the overall electronic community. And when I started doing my PhD back in Germany, my initial project failed because the laser was broken for quite some time. So I thought, we have these microscopes, and they always follow the same principle. So you have a light source, you have a lens, you have the sample, you have an objective, and a camera. And wonder or not, there's like this focal length in the lower end, and you see that the focal length of each lens here is basically following one another. So why is that? You do a Fourier transform from here there, you do a Fourier transform from here there, and another Fourier transform from here there. So you can easily modularize it, not only physically but also computationally. And so we thought, well, let's just do it. So we have these blocks around the cubes, around the modules, so they form cubes. And because we were talking about like history of stuff, so it didn't really start with that. So there was the initial idea to have a small microscope that just images cells in an incubator. So we started, of course, with a small Raspberry Pi. We had to have some focusing. Then we thought, oh well, it has to have some illumination. And then we thought, okay, why not modularizing it? And then it started. So it was a process of like 3-4 years to end up with something that you see here on the table, where you have a kind of large library with parts that have a certain function, like a laser, a stage. There's, for example, also a galvo scanner, or for example, also a module for the open flexure, which is like this pink thing over there. And so you can just hack together parts, and you have a unified system there. And this is then becoming useful because once you have this library, you can just stack the cubes together. For example, having an incubator-based microscope where you have an LED to illuminate your cells. In this case, it's just observation of differentiating monocytes. And which is also cool, you can build that at home. So you just rely on your printer, you print it out, you use stuff you can buy on Amazon, as I did just for today. And but you can also add more complexity. For example, we learned about these fiber-coupled lasers from Honchuan, from the squids, and then you can easily build also more sophisticated microscopes for fluorescent stuff, also for the incubator, or you just wrap the laser with a high intensity laser, and again you can then do this pointillistic imaging I was talking about last time, so that you have the blinking, what you see here eventually, to end up with high resolution. So the thermoplast, which definitely bends at temperature changes, is still like stable enough to have proper imaging at the nanometer scale. So what you see here, the like tubules are in the range of 80 to 100 nanometer in diameter.
And then a comment that I'll make about this, I think the conceptual idea that you should take away from modularity is very much like programming. So if any of you program, you write functions, but the beautiful thing about this is that now anybody else can write that function, which is that one cube. And so this is part of the challenge that we will think about, that as more people write more functions, you can build more and more complex instruments. And all of them are still, as long as your API, like in a function you have an interface where you define very specifically of what inputs and outputs should look like, that cube is a little bit like an API, that you want to break whatever the function is in units of those cubes.
Yeah.
So those little physical, if you go back, I love that picture, if you go back a couple slides, this picture, because this is a library of functions essentially.
Yeah.
And this is why thinking in Fourier optics is actually important, because they are actually implementing a function.
Yeah.
But some of them are optical, but they don't all have to be optical. They can be mechanical, they can be electromechanical. they can be purely electrical, they can be purely mechanical, and there might be fluidic blocks that we'll think about. So I think as a class, one of the challenge we'll do is try to expand that library, because if you expand that library, then suddenly that library is available to a broader group of people.
That's a very good point. Yeah. So I just give around some cubes that are actually not 3D printed but injection molded. So it's just an idea what you could do. So this is like say beam staircase. This is like a laser. This is actually it's a syringe pump. So you always have to think about, okay, how can we fit stuff into the form factor? It also gives another
Maybe if you guys
cube
pass it
around.
that way, just everybody gets
So
the
this is
hands
the
on them.
3D printed version because it has this very nice click effect, because we in the beginning relied on magnets and screws to have some kind of a snap fit mechanism. And yeah. So and in terms of interfaces, I was stressing FreeFX maybe a bit too much for this course, but FreeFX is cool because you rely on a natural API. So you have interfaces that are either real space or free space. So whatever module you design, well, of course it has to fit in this scheme. In this case, it's 50 times 50 times 50 millimeter. And you also have to make sure that the outgoing plane is either free plane or real plane. And so with this, you can
Anyway,
do.
we will lose half the people in US because we didn't choose inches.
Yeah.
Yeah.
That's true.
Yeah.
But I
No,
don't care,
let's
but-
stay with. Yeah.
There's a reason why most of people rely on metric scale.
Yeah,
But
I
anyway.
hate the fact that in optics there are two types of optical tables that you get, and they are all, when all the parts get mixed, it's just, it's a nightmare. So let's stick with what.
Especially since
These
you're doing
cubes.
screws with
Yeah.
metric scale. Okay, so this is a very sophisticated module that Harvard built. So this is called structured illumination microscopy. So this is a very funny trick to beat this formula there. So what you have in the end with image processing and kind of a more array effect, you downscale the actual optical frequency by superposing it with a known frequency, and you just reconstruct the actual frequency. So what you then have in the end is like lambda over 4 NA. So you can have a resolution that is half of what you would expect usually. All in one module by relying on a small projector and lasers and free filters, etc. And what is also cool, that's also something I brought here, like a full setup, is you can build light sheets. What is a light sheet? So the problem of the optical resolution is not only there in the 2D plane, but also in the 3D plane. So you always see that if you take a picture, for example, it's always a projection along the optical axis. So if I were to take a picture right now, I see you, all in one picture. So there's no optical sectioning in a way. So I can clearly identify everybody, which is nice for photography. But in microscopy, if you have a 3-dimensional cell and you see the nuclei and the actin of maybe something that's in the back, that's superposing, you cannot identify, or like you cannot differentiate between different cell compartments. So there are multiple different ways to do that, but the easiest I think is Lightsheet. So how does it work? Usually you just have your cell, you observe it through an objective lens, and you also illuminate that through the same objective lens. So you shine light on it and detect in the same direction. So how cool would it be if you detect like that and you illuminate from perpendicular side, so that you use a light sheet, which is very thin. You select the plane you want to see, and you just focus your objective lens to the plane you want to see, so that everything that's not illuminated is not visible actually. And so there are multiple different ways to do that, all of course somewhat in the cubes. So the easiest is what you see there. It's called OpenSPIM. So SPIM stands for Selective Plane Illumination Microscopy. You have your detection, which is just a typical microscope. So you have a lens, a camera, and then you have a laser, where you form a 2-dimensional sheet with a lens that I think I brought here. It's a cylindrical lens. It means you have a focus along one direction. And you saw also that the laser does not have a perfect round shaped spot. It was somewhat elongated. And the reason is because of laser diets, but we can also discuss about that in a bit. So if I take this here and use the laser to visualize that, then you see already the laser spot is a very bad example because it's not really round. It already has this kind of slice. But if I take this lens here, you can put that, you can make this even better. So this is kind of our light sheet we would use to visualize or like to select the plane of illumination.
So just in that context, if the illumination is this way, this is the object.
Yeah.
You're optically sectioning my hand, and if it was transparent, you're actually imaging from this axis. So what's unusual about it is these implementations of light sheet is a 90-degree or an angular. The object that you collect or image from is different in plane to the objective that you illuminate with.
Right, and there are many different ways to realize that, and there's also one project we're working on right now to visualize plankton in 3D. So what you could also do is like you have a throughput system on the upper hand here. I think it's called like fluid swim, which is 45 degrees. So you just let samples flow through your capillary, and then you have your light sheet illuminating your stuff. And you observe it from 90 degrees to it, and then you basically have a sample sheared by 45 degrees in 3D. And what you see here on the lower left end is just you blow the sample into the field of view of the lens. And what you have here on the lower right hand is something we're working on, which is actually not here, but in the lab downstairs. I call it Holy Sheet because it's a holographic light sheet with rotation. So I think it's I have it from.
So it's holy as in the festival of holy.
yeah, exactly.
With
because
all
it's
colors.
And here it's special because you rotate and you get a three-dimensional shape similar to a CT scan by rotating the sample. And so one challenge for today, for example, could be to replicate this here. So this is a diagram for the light sheet, where you can just build your light sheet and visualize, for example, lens tissue that is labeled with marker. This is then the result with what's downstairs in the lab, or this is what's here. The diagonal shaped image can directly render to 3D, so these are just some beads that flow through the sample plane. And what's, I think that's the algae, and this is then the rotation. That's what you would expect from the plankton. So this is just simulated data. The hologram is in the upper area, and the light sheet is in the lower area. And the actual data, unfortunately, look a little bit different yet. So we have to improve the image quality. So having a capillary rotating stably with flow is actually quite difficult to realize. And so, but still all in the same form factor, having 50 millimeter cube size. So this is in a way very nice because it's standardized, but at the same time it's also a limiting factor, of course. That's how it looks like. The hologram on the right hand side, the light sheet on the left hand side.
And then a comment I want to make is, and if you go back a few slides on one thing that we could literally build today, if you go a few slides back,
Sorry.
I think for folks that don't build microscopes, yeah, right here. For the folks that don't build microscopes, it is absolutely insane for somebody to say, hey, in a few hours, we're just going to build a setup like this. So I think if you're hearing about this for microscopy for the first time and you go to a traditional microscopy context, that would just be, they would laugh at you. But this is the power of modularity, because each one of these sets of functions have already been optimized for, we know exactly what they're doing, and the set of alignment that you spend an incredible amount of time in optics doing, these sets of magnets and the kinematic mounts around these objects, all that mechanics is being taken care for you. So if I know there are a couple of freshmen in the class, if you're hearing this for the first time, that we're going to put together a microscope rapidly, this is the power of a system like this. This is not how traditionally it has been, and this is kind of why, even from a context of, if you have invented something playing with this idea, the fact that finally you manufacture it in a different form factor is also okay. But to be able to rapidly come up with ideas and actually test them and learn optics by tinkering, this becomes a remarkable way of thinking about it.
Yeah, I have a lot of friends who have spent a year of their PhD building a microscope that already exists somewhere else in the world.
Yeah, so
Yeah.
The repeatability aspect in science is a huge issue.
Yeah, I think that's also a good point to just stop it and maybe
Yeah,
think
build
about
stuff.
how to proceed. So what I prepared, like brought, is everything I could have printed until now. So we can always print more and get hands on other things. So we ordered some lenses. Unfortunately, they are like very long focal length lenses. So this is like I think 200 millimeters. So to see an image, actually, I don't know who ever. Well, I think when I did that the first time, it's always like, oh, you see an image on the palm of your hands. So just give this around. You cannot destroy it. It's very children safe. So we have these lenses. We have funny optical elements like prisms. We also have a very huge ball lens, which may be fun to play with. I don't know, like a very huge spherical lens here, where we can see how aberration really matter. We have cameras. We have also mirrors. So, and we also have a list of like challenges. So depending on how much optics you want to do, we can, yeah.
So I think, Benny, the way I would propose is let's cluster into 4 groups. One can be just purely optical components, so people can then circle around. So we'll just put different types of optical parts itself, and if you want to just familiarize yourself with, if you've never played with optics ever, just hold a lens even and play around with it. So we'll do that on one bench. Then let's do some of the semi-built demo systems at the level of complexity where there is like 5 or 6 or 4 or 5 cubes. So you understand the first version of what the minimal optical system.
Yeah.
You got a lens, you have an object, you have a detector. And then on one table we can set up, if you want to understand how complexity scales, let's set up that Lightsheet setup all the way at the back where people just first come and watch and, oh, I get it. The picture that you drew and the physical object, I can identify every single set of the component. And then people can circulate around between different groups. Because I think if we all huddle around one single thing,
sure.
you might not get the visceral feeling. So I divided that into 3. Is there another? I'm thinking of bare minimum optical components as one. Some of the cubes, which are just the adaptation of a component into a UC2 system as one. Then I'm already seeing a mini microscope right there as one, and then we can set up the light sheet at the back.
Yeah.
Which we do as a 4.
Yeah.
Yeah.
And just for those people who are curious, so I think one challenge, maybe something like a homework for those who are keen on doing some CID with the stuff they brought. So everything I just showed is all documented open source. So the question of open source. So I think we have a definition by means of people can replicate it, modify it, and also improve it. And so, for example, if you want to build like this Lightsheet microscope, you go to this web page, GitHub, UC2 Git, and then you find all the different information like the bill of material, how to assemble the stuff, and also how to put stuff together. And one challenge, so for example, I see like an LED torch right there. I see glasses. I think they were just in use. And so the question is, of course, how do we bring stuff into the cube here? So I do that for a very long time, so I know how to do that. But you maybe have seen like the stuff here, like the insert that goes into the cube here. It has always the same form factor, no matter what's going in here. So it's just clicking in here to close the cube, or you just put some screws. And in order to help you build your own design, so this is how it's meant to be used. There's also some help on the way.
Just while Benedict is doing this, how many of you have actually done CAD yourself? Like just any CAD program. So I think this is also kind of another fun thing to think about is you can choose your favorite CAD program. If you have never touched CAD, we will do a teach me something session just separately itself, and then any one of you could teach that for people who might not have done CAD. we could choose and share some of our favorite CAD softwares, and especially free softwares as well on Discord as well, because for many of the things, and again, if we really want to exploit 3D printers for your projects, eventually you have to dive into CAD. So this is a great excuse if you've never done it. It really is worthwhile, and you can choose, and again, when we build teams, we will kind of sprinkle capabilities. So there is one person who's very familiar with it, but the purpose of this class is to also embody all the sets of skills in one person. So this is a fantastic excuse. A UC2 module is a great reason or a great excuse to even just learn CAD. Because you are already given a part and all you're doing is modifying it rather than starting from scratch.
Exactly, yeah. And so there's, as I said, little help. So we have set up a small repository where you can learn what's the dimension, we also made some templates for at least a few CAD software, and also we have a little tutorial where you can then just, oops, not here, here, I should have clicked there. So we, for example, have this camera here. It's called RDcam. It's a USB webcam, and for this we wanted to have a small module. And in order to not do that all, in order to multiply the effort, it's always good to have like a tutorial where you can have like step by step. At least how many people watched it? Oh, 14. So since yesterday. I wonder who that is. So yeah, so it's
We'll double that number just today.
we'll see. Yeah, so I think this session now is pretty open. So if you have any ideas for like a fancy, crazy optical setup which you would like to see inside the modules, I think it's also just fun to discuss how could you build, like, I don't know, somebody was approaching us to ask for like a whole stat imaging microscope. Like, how would you do that where the laser alone is like 100K? But it's like just fun to think, okay, what are the core components of an optical system, and how could you engineer it the way that it's becoming frugal? So for example, like the Lightsheet. So what is the core component what we can get rid of so that it becomes more approachable or more low cost or something like that?
And I think the one thing that I would like to see and emphasize, and if we end up using some of the UC2 components for projects, is think beyond microscopes. Microscopes is only one view of the world into where optical solutions are very empowering, but the system is far broader than microscopes. So just, we'll talk about spectrophotometers and a couple other measurement tools. And so depending on slowly as people's projects start maturing, this will become it's like a breadboard for you to test out an optical idea. But it doesn't have to be microscopes as we discussed.
No, exactly.
So should we divide up parts, and then I think this is going to be the open-ended session. You can also just find people. We'll kind of lay out 4 groups, and one thing that would be very valuable is we can leave that schematic up online, up here. So once people have looked through the sets of components and you walked around and you feel familiar, then one group can sit down and kind of say, oh, do we have enough part to actually build a replica of that minimal system itself? You could choose any kind of a very simple system, but depending on parts and what replicates we have. And then the other part of that would be is for the more complex system, you can also just have conversations right there about the electronics itself. What does it mean? Because all of these systems are being computer controlled, so you want to walk through all the way from you have power going in here, what are all sets of components beyond the optical components? Yeah, so maybe 4 groups. Bene, you should split up the material that's on that one table into 4. And then on the bare minimum optics table, which will be this one, there are all kinds of fun things that some of you might not have done with optics. So we'll kind of go around and think about any observations that you might have made. Like, hey, I saw this pattern. How do I explain that? Why is it that I see this? This is also another fun way of learning optics. Because we are visual beings, if there is anything that you have seen with your eyes that you cannot explain, the bare minimum optics table would be the table to actually just have those types of conversations as well. It's like, yeah, I think, you know, when you look in night sometimes and squint your eye, you know, have you all done that? When you squint your eyes, you can see lines. So you're gonna figure out why that happens. Bring up your questions on this open-ended optics table, the one that we'll have the components from.
So you could also just say everybody does the same thing at the very beginning. So let's say everybody builds a telescope to get familiar with the system, and then we can spread to different places.
Yeah.
So, and again, like we have a different, like we have a whole thread of different tutorials where you can also just go through it individually. So I'd say since we have only limited number of parts, maybe we gather now 4 groups. Let's say like, this is many of the lab. I don't know whether our lab will stay here or not.
Yeah, no, let's just divide it in 4 and people will choose which station they want to go to first. Ideally, everybody will go to all 4 stations. So this station is the bare minimum optics station. That station is UC2 parts. Let's put a minimal UC2 system on that table, and then the light sheet can go all the way in the back. And then choose whatever you find interesting, and then we will all just circulate around, depending on your level of where you want to dive into the space. Pranav, we're going to say bye, so that we're going to cut the Zoom. Now for the next part, you need to be physically here, so. Bye, Pranav. Yes, sorry, go ahead.
Should we have the minimal optics table also be the stuff that we brought table? where
That's
we take
correct.
optics?
The minimal optics table is also the table. I had asked everybody bring something that you are willing to break and try to open and understand. So just bring all of those things here too. And if you're sensitive about you want to open that part yourself, we will just first discuss the things that you bought, how they work. Because this is such a rapid-paced class, I want to make sure that all kinds of optics discussions can happen as early as possible. I think that's a great idea. I'm hoping some people brought some unusual things. So just whatever you got, you can bring to this table itself. And then maybe Anton, you can, I'll take the optics components over there. You guys can take that mini system was going, actually the mini system was going here, and then Benedict, you could first start with that Lightsheet system over there to walk people through what that works. I'll start on this table, and then we can just all circulate around. And then questions that you have for anybody, just find people. So this will be much more of a floating kind of a session now. So where are the parts? I guess they're just all here. And the cubes go on this table. So cubes and parts are here. Yeah, so that's good. How much does this all cost?
$5.
Okay, yeah.
Nice.
Yeah. I am expecting it to roll off pretty soon. So. Oh, just 101 of optics is don't touch the optical surface with your greasy hands. Just this is a common thing. Of course, it can be cleaned pretty easily, but whenever you are handling, try to handle any optical thing with the side. And then all the parts, you can all bring it over there. Okay, so the UC2 parts are here.
You're not coming here? I don't know. So which are the stations?
So here's the one station. This one I think is UC2 parts. Is that right?
Yeah.
And then we'll have Lightsheet, I think, back here. So Lightsheet is like a
All right. All right. Yeah, let's do that carefully. So the one thing you want to do is if you want to get started on that, set yourself up, get a set of tools, and once you've opened the lid yourself, you walk around.
eliminate an entire domain, but not like the default is like
Okay, so these are the small parts that we then we assume that you can move that
I'm gonna go there, but that's like our schedule.
And then also the lights itself.
Yeah, sure. What do you use it
Because when you look from here, it's always puzzling. It's not exactly the same, but they're close.
So the I think
Yeah, like the blue, because this only indicates that, but this point also identifies how the characters you know what you're doing.
But for today,
Yeah, so we'll just open it to the actual
46. I would say like try to get through all of
are we having
Let's figure this out. What it looks like.
Trying everything at once. So figure it out. I'll get back to you.
That's why SLRs and have a type of that allows you to see
the matter, the fires,
right there is one of the spots. Okay, go up there with
And then the question for you, Manu, just in terms of organization of these structures, we have 4 stations. I don't know which station I should be at.
You
This
should
one
just
seems
hang
like-
around, like treat this as your own learning session.
Yeah.
And then
Totally.
when people build questions, you can just find those sets of questions.
Okay, perfect.
Yeah, but
perfect.
just now it's everybody is floating and thinking, and then common sets of